We're going to start the final session of today with a talk from Maria Chekhova. Maria is head of the Quantum Radiation Group at head of the Quantum Radiation Group and Signal Photon Technology at the Max Planck Institute for Science and Technology of Light in Erlangen in Germany. She also holds the chair of Quantum Electronics at Moscow State University. And she's going to talk to us today about SU11 nonlinear interferometers.
Thank you very much. And I would like to thank John and all the organizers for inviting me here. It's my first time in Bristol, and thank you for organizing this workshop and the nice weather as well. I will speak about SU11 nonlinear interferometer, and of course I have to explain what it is. So I will do it first thing, explain what is SU11 nonlinear interferometer, and then I want to show some interesting features, such as phase sensitivity better than short noise limit allows, loss tolerance due to amplification, and some ideas towards sensing orbital angular momentum and towards enhanced subshot noise imaging. That's what we haven't done so far, but we are working on this. All right, so nonlinear SU11 interferometer, how to explain? The term was coined 30 years ago, so I'm not responsible for this. And the idea is that if you have a Mach-Zehnder interferometer, this is something that we know, yeah, and then replace the beam splitters here and here by optical parametric amplifiers, which can be through parametric down conversion or through four-wave mixing. And because these elements perform, instead of SU2 transformation in terms of group theory, SU11 transformation, this is called, first of all, one can say that it's nonlinear interferometer because there are nonlinear crystals instead of linear beam splitters, and second, that it is called SU11. How it helps us to make the phase measurement better than with coherent light. To do phase measurement, of course, one uses an interferometer. But if you have a linear interferometer, a usual interferometer, and you want to sense some phase change, for instance, there is a gravitational wave, and we want to record. We want to measure the phase delay or the phase change. One can do it by direct detection, and depending on the phase and the interferometer, the detector will detect different photon number depending on the phase. So typically sinusoidal dependence. How to calculate the phase sensitivity? It's easy. So we have to, what we measure is the photon number or the intensity. So the accuracy in the photon number should be divided by the slope, and then we get the phase accuracy or phase sensitivity using this simple formula, the delta phi is delta n over the derivative. And from this simple argument, one can infer that for coherent light, if we send coherent light into this interferometer, then a limit comes. So the ultimate phase sensitivity is given by this so-called short noise limit, because coherent light is what gives us short noise, the minimum noise, sort of. This short noise limit is just 1 over square root of the mean number of photons in the interferometer, the mean number of photons hitting some element that is displaced. Can we do better? And yes, quantum optics says that yes, we can. The ultimate limit achieved in quantum optics can be lower than this short noise limit, and it's called the Heisenberg limit. It's not exact, but the best phase sensitivity scales as 1 over the mean photon number in the interferometer, and of course it's smaller, it's better. It's known that this limit can be achieved with some very exotic states, like null states, but these states are difficult to work with. They suffer from loss a lot. And as an alternative, it was known, starting from these old papers on SU11 interferometer, that at high parametric gain, this device can actually reach the Heisenberg limit, provided that there are no losses. So these two parametric amplifiers, and between them there are no losses, and outside there is also no loss. So ideal detection, ideal interferometer. Then we can reach the Heisenberg limit. However, in reality there are losses. And there are two types of losses. As I said, internal loss, here mu denotes the transmission of the interferometer. So this includes the faces, the losses at the faces of the crystals, whatever dust you have in between, and the non-ideal mirrors and so on. And then there are external losses of quantum efficiency of the detectors. And in principle, this is the bottleneck, because sometimes we need to measure at wavelengths where quantum efficiency is not high. Then I will introduce R here. R is what we call parametric gain. So to give an idea what it is, I would say that the number of photons after a parametric amplifier is given by the hyperbolic sine square of this parametric gain. And it's basically exponential function of that parametric gain. The interferometer can be seeded externally by coherent light. At the output, one can do homodyne detection or direct detection, but the result is more or less the same. So the loss destroys our ability to achieve the Heisenberg limit. In our scheme, what we realized in the lab, we do the very simple version of this interferometer. What we do, we put the two crystals with parametric down conversion, so two Chi2 crystals, into the same pump beam. R is again the parametric gain, the number of photons at the output scale, not scale, but per mode, it's the hyperbolic sine square of the gain. And the phase can be changed by just displacing the crystals with respect to each other, because there is air between the crystals, and air has dispersion. Although air has weak dispersion, but strong enough to have the refractive indices for the pump propagating from the first crystal to the second, and for the down-converted radiation to have different refractive index, to have different phase delays. And therefore, depending on the distance, we can change the phase in the interferometer. Just to give an idea, the period of this dependence is about 3 centimeters. So at crystals close to each other, they amplify each other. At a distance of about 3 centimeters, they de-amplify each other. And in the collinear direction where we look, where we put our detector and we measure just the intensity, in the collinear direction, if the distance is about 3-4 centimeters, there is nothing emitted in at the center. So in the collinear direction, there is a dark spot. So what happens when we change the distance between the crystals? We change the phase. The number of photons starts to increase very, very strongly. And compared, we use the formula that I showed. So the uncertainty in the number of photons should be divided by the slope, and we get a phase sensitivity. And if we compare it to the usual linear interferometer that is called SU2, the same picture, but the amplitude is much smaller, because here, depending on the phase, the amplification is non-linear. It's exponential amplification. And that's why the slope is higher, the derivative is higher, the phase sensitivity is better. However, I forgot about the noise. I don't want to cheat you. The noise, of course, will be also higher than for the linear interferometer, but there is a range somewhere here near the dark fringe where the noise is still about the shot noise, still low. And so the combination of these parameters leads to this dependence. So this is phase sensitivity delta phi compared to the shot noise limit, and depending on the phase. And you see in the middle, the phase sensitivity is very bad because of this derivative being zero. But on the left and on the right, there are regions that we call supersensitive phase ranges. And here we can go below the shot noise limit, and the extent to which we can go below it is given by the loss inside the interferometer, by the parametric gain of the crystal, and of course by the quantum efficiency of the detector. Now, the trick we did recently is that we started to unbalance the gains of the two crystals. So we sort of pumped the second crystal stronger. Here I write R1, the gain of the first crystal is positive, the gain of the second crystal is negative. This means just that phase is such that we are near the dark fringe, so that the emission from the first crystal is de-amplified, is like suppressed in the second crystal. And we want the second parametric gain to be higher in the absolute value. for the reason I will explain in a while. And it so happens, here is just a theoretical calculation, that if the quantum efficiency of the detector is not 100%, or it can be 30% here, can be even 10% here, we can always achieve the value of phase sensitivity, the delta phi, the same as for ideal detection by increasing the gain of the second parametric amplifier. And the same, so the first plot shows the phase sensitivity versus the gain of the second crystal. The blue curve is for quantum efficiency 100% unity, and depending on the gain, of course, we reach some limit of phase supersensitivity. But for worse quantum efficiency, well, things are not so good. But we can always, by increasing the gain of the second amplifier, we can reach the same situation as for the ideal quantum efficiency. And the second plot relates to the width of this supersensitive phase range. The same situation. If quantum efficiency is bad, then the range reduces, but we can always overcome this loss by increasing the gain of the second squeezer or amplifier. How it works? Well, just some explanation, also hand waving, not with formulas, but hopefully it's clear. So this is the same system, squeezer, and the second I will call anti-squeezer because it works oppositely to the first one. Here, at the input of the parametric amplifier, we just have vacuum, in addition to the pump, of course. We have vacuum, which becomes squeezed vacuum at the output of the first crystal. The gain is high, so we get some kind of squeezing. And then this squeezed vacuum has a phase. And the phase is given by the orientation of this ellipse. So what is shown here, I can say it's the Wigner function of the radiation mode. And this ellipse rotates if I change the phase of this squeezed vacuum. And the extent to which the phase is measurable is given by the overlap of these Wigner functions. So for instance, if we look at the blue and the red states, we can distinguish, we can resolve the phase between them if they are not overlapping. And if we try to measure these states without amplification, it's in principle very good because they overlap small compared. The overlap is small compared to the overlap between two coherent states with the same photon number. But if our detection is lossy, then the loss spreads the ellipses in this direction and shrinks them in this direction, and they become overlapping. They become indistinguishable. It means that loss destroys our ability to resolve these phases. However, if before registering this flight, before measuring, we apply another anti-squeezing. So first time we squeeze, we stretch this state along the horizontal line. But second time we stretch it along the vertical line, and then the result will depend on the phase. So here I plotted what should happen with these two ellipses if I apply a stretch along the vertical line. The blue state becomes much more squeezed than the red state, and the figures do not overlap anymore. So they overlap not completely, and even after the loss is applied, they are still distinguishable. These states still distinguishable. Well, this is part of the general principle that parametric phase-sensitive amplification helps to protect some quantity against loss. And in other words, I can formulate, I forgot to say that the short noise limit is still defined by the number of photons inside the interferometer. And whatever I do outside, or whatever I do at the output, does not affect the short noise limit. That's why I can overcome it. So, in other words, I can say that the quadrature responsible for the phase information, it's this quadrature, the P quadrature. And it is amplified before detection, and this amplification protects it from loss. Okay, so this is our experiment. We used two BBO crystals pumped with picosecond pulses with rather high energy, 0.1 millijoule per pulse. Of course, the gain could be up to 5. These are. We changed the phase by changing the distance between the two crystals. After rejecting the pump beam, we did filtering. This is important because parametric down conversion, this is just parametric down conversion. It has infinite spectrum in principle, in angle and in frequency, and one can't just collect everything. So we had to do filtering. We put a lens and an aperture in the focal plane of the lens, and then we put spectral filtering, band pass filter, afterwards we registered everything by photodiode. We used post-processing to make our pump less noisy, so we selected pulses that had fixed pump pulses that had relatively fixed energy, because the pump pulses energy fluctuated. Finally, to define, to measure the short noise limit, we just removed this crystal, or rather we tuned it out of the position where it produced photons. So we rotated it around the pump so that it didn't contribute into parametric down conversion. And then with an avalanche photodiode and filters, we measured the number of photons that was inside the interferometer passing through this filtering setup. And this way we just calculated the short noise limit. These are the results. First, we consider the situation where we change the first parametric gain, the parametric gain of the first crystal, and keep the second parametric gain constant. The numbers of photons in the interferometer being about 2 and about 11, which is not a lot. Yeah, I should explain, of course, that all this technique works at low photon numbers so far. Maybe it can be upgraded to stronger beams, but here it was just 2 and 11 photons. And we overcome the short noise limit for both cases, but it's easier to overcome it when inside there are not so many photons. 11 actually was the maximum number of photons we could work with. And here the opposite situation, we have the first parametric gain the same, and we change the second parametric gain, and here we see that when they differ, R1 and R2 modulo differ not so much, like in the blue curve, we are above the short noise limit. But to get below the short noise limit, we have to make the interferometer very unbalanced to pump the second crystal stronger. And finally, how we demonstrated tolerance to loss. We changed additionally, we reduced the quantum efficiency. Initially, our quantum efficiency was 77%. That was the quantum efficiency of the detectors plus loss, and so on. But we could further reduce this quantum efficiency by just putting neutral density filters. And for the situation where the two parametric gain values were about the same, well, 50% different, we couldn't overcome the short noise limit at all. When they were differing about 2 times, 1.9, we could overcome the short noise limit with the best quantum efficiency, but then our data became worse and worse, and the supersensitivity was lost. And finally, when the ratio was higher, we could see supersensitive phase measurement up to 17% of quantum efficiency. All right, so now what we want to do next, we want to sense the same way as we sense the phase with this interferometer. We want to sense something else, and this is orbital angular momentum. I will remind what is orbital angular momentum. This is about beams that have not a flat phase front, but a sort of spiral phase. Imagine there is a beam here. Try to show the beam propagating towards us, and usually, well, these beams have to have a donut shape, because otherwise there is a singularity. And along this donut, the phase changes. So this is the field with the azimuthal angle phi. The phase changes, and the more it changes, the more each photon carries orbital angular momentum. This is an interesting physical quantity. I'm not going to dwell on this, but just want to say that we want to see how SU11 interferometer can sense this phase also better than in classical optics. So for this, we made a different construction of the interferometer. The idea is that we want to have a broad angle interferometer, because these beams have large angles. They are not very collimated, yeah, as you can see from the drawing. And so we needed to amplify or de-amplify large angles as well. And for this, we designed a scheme where the parametric down conversion from a crystal is imaged into the second crystal by means of 2F to F system. So there is a lens, everything is imaged into the second crystal, the phases change somehow. Actually, we folded this scheme. I will not show the real experimental scheme. We folded it. And at the output, we looked at the result. So what for? We want to achieve uniform amplification for all angles of emission. We think that this interferometer will be stable, so its orbital angular momentum spectrum will not depend on the phase delay between the two crystals. And finally, we want to see subshot noise sensitivity to orbital angular momentum perturbation. And these are very first results. So this is the image after the second crystal. We see that there is the whole field, no fringes. The whole field is amplified, and depending on the displacement, this is the piezoelectric displacement of one of the mirrors. We see de-amplification, amplification, so far very weak. I mean, visibility is not so good. And this is what happens when the lens is, in the picture, this lens is misaligned, and then there are rings appear, but we want to avoid these rings. So this is very first result. And now I change the gears during last 3 minutes, maybe 4 minutes. I want to explain what we have also for the future. Our planned project is how this parametric amplification that makes things tolerant to loss, that protects fragile quantum information against loss, can be used for imaging and sensing. So there is an old idea, relatively old, 10 years ago, of subshot noise imaging. If the object to be imaged, or whose absorption we want to measure, or some spectral line that we want to sense, is placed into one of the twin beams. This is signal and diver beams from a two-mode parametric amplifier, and there are photon number correlations between the two beams. And then if we register the two beams with two detectors and subtract the signals, we can image this object, if it is very weakly absorbing object better than short noise, better than in classical optics. And the first experiment was made by Marco Genovese group. So I will not go into details how the setup was made, but really some object which was a pi letter was put into one of the twin beams in parametric down conversion, and they subtracted two images basically, and they saw that the twin beam image got better quality than classical images. And a very similar work was done here in Bristol, so I want to cite it as well, on measuring absorption, weak absorption. So my point is that we can improve this scheme, because the drawback of this scheme is that it's very sensitive to the quantum efficiency. As all subshot noise measurements, it's very sensitive to quantum efficiency. Here I plotted the so-called quantum advantage, so what we gain by using the twin beams, the photon correlations, versus the quantum efficiency. And you see that at low quantum efficiency, there is no advantage. The Q is below 1. But the problem is that sometimes we need to image in difficult ranges, like terahertz, middle infrared, and so on. And in this case, as a solution, we want to apply this parametric amplification before detection. This is the scheme. So after the object, in both beams, we need to put a parametric amplifier. it has to be phase sensitive, so it has to be single mode. The phase should be the same in two amplifiers in both beams, but it can be any phase. We have some setup in mind, of course, but now I show it just very general, and this is the result of the calculation. For unity quantum efficiency, this quantum advantage is about 8, 9. So we can achieve signal-to-noise ratio about 9 times better than classical limit. If the quantum efficiency is 0.1, then immediately we have no advantage. But by increasing the parametric gain of this second amplifier, we can always achieve the same value of signal-to-noise ratio as for ideal detection. This, of course, works only for small absorption. Here, 1% absorption, and here it's 25 photons. So the case of weakly illuminated, very faint object. So before I conclude, I want to thank my group. Mathieu Manceau was the main experimentalist, and Gaetano Frascella just started new experiments and theoretical support from Farid Khalili. And recently we got 2 new helpers, Valentina Verchenko and Evgeny Mikhailov. We look for a postdoc. And finally, conclusion. So I hope I convinced you that the C11 interferometer provides subshot noise phase sensitivity, that amplification, additional amplification at the second stage makes it tolerant to losses, and the same strategy can be applied for imaging. Thank you very much.
Thank you for a very interesting talk. Paper's open to questions.
Yeah. So could you go back to the when you moved the lens?
I will show you the real scheme now.
Okay. Yes. So first of all, which lens do you move? The one is the one between?
Well, this is the real version that we use in experiment. You see, it's a little bit more difficult. We use a single crystal. We pump it. Then we, the 2 channels, instead of 2 crystals, there are 2 channels. First channel, the pump goes back, this is a dichroic mirror, the pump is reflected back into the crystal and creates the second emission. The other channel is that just the parametric down conversion goes, is reflected from a dichroic mirror, then is focused by this lens into the same crystal. The distances are focal length, focal length. And this scheme is equivalent to that one, so we move this lens, this one. If it is not properly placed into at the focus of the crystal, then we have rings. If not, we have.
Yeah. So my question is actually, so which values of L can you detect measure very carefully?
Okay, so far we didn't use this lens scheme, and we were able to have the spectrum of orbital angular momentum up to L equal to 10. And now we hope to go to much higher values, like 30 probably, because a single crystal emits really broad spectrum with a very broad distribution over OM.
Yeah. So you can do actual imaging.
Yes.
Question from James.
Thanks. So this, having multiple nonlinear crystals reminds me a little bit of these Dickey radiance experiments. So where you see this like increase, quadratic increase in photon generation rate with the number of crystals. So is there a chance you could see something crazy happen with multiple crystals?
Well, I believe so. As any multiple beam interferometer is better than 2-beam interferometer. You have, instead of sinusoidal dependence, you have these Airy functions or whatever, yeah, they are called. And of course, everything improves, but also difficulties increase, because currently at every crystal we lose about 1%, I think, loss. Yeah, there is about 1% loss. I don't know what happens if we have many crystals, but yeah, we had this idea and we wanted to do it. Yeah.
John.
This amplification method, is it so when you're making some sort of measurement and you're getting a subshot noise measurement, you're counting resources by the number of photons that travel through the sample, So I can see that outside the interferometer, if you use a parametric amplifier as the output of the interferometer, you get protected against, say, detection loss. But is that also protecting you against loss inside
No,
the interferometer?
no,
So
no.
inside the sample
Not at all,
itself?
not at all, no. But we hope that inside, of course, some loss is inevitable. Like we have 2% loss. I'm sure we can have 0.1 or 0.2% loss by using fresh crystals, good coatings, and so on. But nothing can protect against it. Well, at least this cannot protect against loss.
And the other point, is just a comment, is that if you're doing one of these two beam schemes where you're then recombining them, those beams don't have to be the same frequency, so
No.
you can sense at one wavelength, which you've got a good detector for, sense with one wavelength where you've got a very poor detector for by measuring at the other wavelength where you have a good detector.
That's true. Actually, well, if here I misalign one of the beams, so imagine the yellow beam now does not pass through the pump in the second crystal, then I obtain this induced coherence effect, another version, where you can look at the yellow beam at the interference in this beam, provided that the red beam is common. So this is a modification, and this is used for this sensing without detection, with undetecting photons. Yeah.
Let's thank Maria again. Thank you.